In this, let's begin seeing the battery voltage architectures in passenger cars. So electric vehicles are built with different voltage architectures, depending on their design, on their purpose, and also the requirements that this vehicle have. These are the common voltage levels that are used in passenger cars, and also these voltages are aligned to various types of vehicles. First, we have the 12 volts and 24 volt systems that are the traditional voltage levels used in internal combustion engines vehicles. These voltage systems, these low voltage systems, are used to power low voltage demand components such as the lighting, the entertainment systems, and the different sensors that the vehicle has. These low voltage systems are present as well in most of the electric vehicles, but they are also supported by higher voltage systems, and we will see later on. Then we have the 24 volt systems, and these are commonly found in mild hybrid electric vehicles. This architecture supports basic hybrid functionality of these vehicles, and it bridges the gap between the traditional 12 volt systems and a full high voltage battery system. Then we have the architectures that are working at between 200 300 volts. These are commonly used in hybrid electric vehicles and are used to power electric motor and to charge the batteries in these hybrid systems, and they work alongside with the internal combustion engine. At the end, we have the 400 and 800 volts architecture. They are most commonly used in battery electric vehicles. It means that fully electric vehicles, and they offer a very good balance between the efficiency, the power, the compatibility with within this voltage and the charging infrastructure. For instance, we have that the 400 volts is the most commonly used architecture because there is a lot of charging infrastructure already in place for this rating voltage. And the 800 volts is mostly used in high performance EVs. Here maybe we can see that as the vehicle electrification progresses, the trend is shifting towards higher voltage systems to meet the demand of having fast chargers, also of having high efficiency, and to in general have a better performance in the systems. Also, each of these voltage levels serves specific purposes, and they are tailored for very specific vehicles needs. So the selection of the voltage demands also a good balance between performance and cost. In the next slides, we will review each of these architectures in detail. So let's start with the mild hybrid electric vehicle. These are type of hybrid vehicles that combine the traditional internal combustion engine with a very small electric systems, and this system is used to enhance the efficiency and reduce the emissions in the vehicle. Unlike the full hybrids, these vehicles cannot run only on electric power. Instead, they use the electric system to support the engine during very specific conditions, and they are used to improve the overall systems. This is the architecture of an Audi A3, that is a vehicle that is a mild hybrid electric vehicle. And here we can see some of the key components. So as you can see, this type of vehicles introduced a 48 volts battery that we can see over here, alongside with the combination of a 12 volts battery that usually is the traditional lead acid batteries of the internal combustion engines vehicle. These 48 volt systems will power high demand components, and also we support the key hybrid functionalities, for instance start-stop systems and regenerative braking to recuperating energy when the vehicle is braking. In red, we can see the 48 volts wiring of the system, and in purple we see the 12 volts wiring. As you can see, the 48 volts power bus also includes this motor or the generator that will provide torque assistance during the acceleration, and also this motor recuperates and captures the energy during the braking. And then it is stored in the 48 volts battery. Also, this energy is stored and used for charging the 12 volts battery that we have over here. Between the 48 and the 12 volt systems, we have the DC-DC converter that connects both systems and allows the 48 volts battery and the motor and generators to charge the smaller battery and to power low demand systems like the lights, the different sensors, and so on. By reducing the workload of the combustion engine, these type of vehicles are characterized by consuming less fuel, and also this is very interesting in the scenario where we have stop and go traffic. In that case, the fuel consumption is significantly reduced. By combination with that start-stop functionality, on top of the torque assistance, the vehicle also reduces the carbon footprint. That is very important. And the complexity of this system is reduced. It is a low voltage system, so it is not very complex. It is affordable, and it is way much more affordable than, for instance, a fuel hybrid or a battery electric vehicle, making them very attractive options for consumers that want to transfer to greener technologies but maybe do not have the budget for doing so. This then is the entry architecture, voltage architecture for electric vehicles. Then we have the hybrid electric vehicles, and in the hybrid electric vehicles we combine the benefits of the internal combustion engine with the electric system, and this dual system operates in combinations to again enhance the fuel efficiency, reduce the emissions, and to deliver in general a better performance compared to the conventional vehicles. What are the key components here? And the most important component that we introduce is the high voltage battery that you can see in the rear of the vehicle. This battery will store the energy for the electric motor and also to power auxiliary systems, and this battery typically operates between 200 and 400 volts. Next to it, we also have the electric motor that you see here. This motor will provide propulsion and also torque assistance that at the end reduce significantly the workload of the combustion engine that we have over here. And between the battery and the electric motor, we have the power electronics. That includes the inverter that has the functionality of translating the DC voltage from the battery into an AC voltage for the motor. Also, there are some other power electronic systems like DC-DC converters to step down the voltage for loads, and the charger of the vehicle, onboard charger of the vehicle as well. The high voltage battery can be charged in several ways. We can charge this battery using, for instance, the combustion engine, and this engine can drive the generator or the motor that can act as a generator to recharge the battery when it is needed. That's one of the ways we have to charge it, to charge the battery. The second way is the regenerative braking, that as we mentioned is when the energy that is generated during braking is captured and then stored back into the battery. And the third one is specific to plug-in hybrid electric vehicles. There are some type of vehicles that includes a charging port that we can see, for instance, here. And this charging port allows the battery to be charged from an external power source. It is not the case of all of the vehicles. There are some that do not include this charging port, and in those cases the battery is only charged via the combustion engine or the regenerative braking. These vehicles are also characterized by having two operating modes. We can drive this vehicle only using the electric power, and in this case the vehicle will only use the power that is being stored in the high voltage battery, and it is ideal, for instance, for low speed and short distance travel, such as in the city and city driving. On the other side, we have a combined mode, and in this case both the combustion engine and the electric motor work together for higher power output and also for high acceleration, and in highways it is the mode that we will be employing. I think so. This describes a little bit one vehicle, and this here is the structure that we have of the Audi A8L, and also here you can see the high voltage bus that goes across the vehicle, are all the orange lines that are the wiring that you can see over here. The hybrid vehicles are very effective, and they are a step towards the electrification of the vehicles. They offer a significant efficiency, and also they have important environmental benefits without sacrificing the convenience of the fuel, and also without depending on the charging infrastructure that might be limiting the adaptation of electric vehicles in some regions. So it makes them very, very interesting. And finally, we have the battery voltage architectures. And here we have also a high voltage powertrain that you can see in this slide. This is the Audi Q6, is e-tron, and this vehicle, unlike the hybrid systems, they rely only on a high voltage battery to power the full vehicle. And this design eliminates completely the internal combustion engines, and that will result then in zero emissions and in some very simplified vehicle architecture. The battery electric vehicles usually operates at 400 volts. 80% of the vehicles that are sold worldwide operates at this voltage rating. Although there are some high performance models that are already working at 800 volts. This in particular is one of the examples of 800 volt systems, and there are some cutting edge technologies and cutting edge systems that are exceeding the 900 volts, even the 1000 volts. These systems and the high voltage system do not power only the electric motor, but also they power auxiliary components, like for instance the air conditioning, the heating, and lighting via DC-DC converters. All of these systems work together to supply completely the vehicle independently and autonomously. So what are the key components of the battery electric vehicles? First, we have the high voltage battery pack that you can see it's very big and actually is almost half of the size of the full vehicle. And this is the primary energy source of the full EV. Then we have the electric motors, and in these cases, to drive the wheels, we can have one electric motor, or we can also have one motor in each of the axes. That is this case. As you can see, we have one drive unit in the front and another drive unit that is on the rear of the vehicle. Also, we have the onboard charger that is here close to the battery, And this onboard charger converts the AC that is coming from the grid into DC to power the charge and to power and to charge the high voltage battery. We have the charging ports. This vehicle in particularly, as you can see, has two charging ports. One is the socket for AC charging and the other one is the socket for DC charging. The charging port supports different levels. In this case, we can have three different levels of voltage. First, we have the standard AC charging, that is where this socket takes place, and in this case we will be charging using our household outlets. Also, we can have faster AC charging using higher power outlets that are specific for commercial or industrial facilities. And on the other charging socket, we allow the DC fast charging. The DC fast charging allows us to connect directly a DC power source that will connect directly to the battery, and in that way that allows us to have rapid charging and significantly reduce the charge time of the vehicle. Besides of that, we have the power electronics that are alongside the vehicle. Here we have some power electronics in the front axle. We also have some power electronics in the rear axle, and we also have some power electronics for charging and across the vehicle. And this power electronics includes, for instance, the inverters that convert the DC to AC, as well as DC-DC converters for auxiliary systems that are in the vehicle. And finally, also we have the regenerative braking system that will capture energy during braking and feed it back to the battery, improving the overall efficiency. As we can see, there are also some other components, high voltage components, like the high voltage compressor, high voltage air heater. All of these are auxiliary loads and auxiliary systems that are powered by the high voltage bus that goes across the vehicle. As was mentioned at the beginning, one of the key trends in electric vehicle development is the shift that we are having towards higher battery voltage. And this evolution from 400 volt systems to 800 volt systems and beyond that is driven by the need that we have for faster charging, and also to improve the efficiency of the system and to have better performance at the end. So here I want to explain you why higher voltages are becoming essential in the EV design. To understand the benefits of increasing the voltage in the electric system, let's first take a look at the relationship that we have between the voltage level and the size of the conductors. This comparison is illustrated over here, where we are examining the conductor cross-section for different voltage levels with the same power loss. So the electrical power loss in a conductor is going to be primarily due to the resistance and the current that is going through that conductor. For the same power output that we have in the conductor, increasing the voltage allows us to decrease the current that will go through that conductors. This is because if the voltage increases, the current needed to deliver the same output will be reduced based on the basic power calculation of the system. And lower currents means on the other side that we will have less heat generation, because the resistance of the wiring will be lower, and at the end this will reduce the energy loss in our system. It also means that we will have smaller conductors and that the physical dimensions of the wire will be significantly reduced. In a 400 volt system, for instance, the current is higher for a given power output, and this will require thicker cables to prevent the overheating and to have excessive power loss. In an 800 volt system, the current is going to be halved for the same power. It means that we will need thinner cables, and at the end we will not increase the power loss. All of these give us many advantages. One is that we will be able to have faster charging that will allow us to have high energy transfer with limited current to our systems. Also, that means that we will charge our vehicles in shorter times. Also, we will have a significant weight reductions. Thinner cables reduce the overall vehicle weight, and this improves the efficiency and the range of the vehicles. We have also material savings. Less copper and less aluminum that is used in all of these wires will reduce the general material cost of our vehicles, and also it will make easier the installation of the systems, given that smaller cables are way more flexible and we can easily route them through the vehicle. So these are some of the advantages that we have with these vehicles. But there is nothing perfect, and usually we have a trade-off between the advantages and disadvantages. The problem that we have then with this new trend is that higher voltage will also require advanced insulation materials, specialized connectors, safety features, and in overall the systems that will work at higher voltage will need special components. So all of this will increase the energy safety and also will increase the costs of the infrastructure that is needed in these high voltage components. Also, we have that the existing infrastructure that we have for charging is optimized for 400 volt systems, and the adoption of higher voltage systems like 800 or 1000 and even beyond requires to upgrade all of those charging networks. That comes also with high costs, and also requires a lot of investment that may pose additional challenges to the adoption of these technologies. And finally, as the voltage increases, managing the electromagnetic interference, for instance, becomes more complex, and that requires careful designs and also more challenging technical more technical challenges that engineers need to consider in the design stage and in the implementation and so on. Let's examine the architecture of this Chevrolet Bolt as one of the examples, just to understand what are all the components and to highlight some of those. This is an electric vehicle that works with a lithium-ion battery pack and operates at approximately 355 volts. That is typical in many battery systems for EVs. This model, the battery model, it's then controlled by the battery energy control model. This system will monitor and will manage the performance of the battery. Also, it will handle functions like the temperature control, the state of charge monitoring, and overall it will ensure that the battery operates efficiently and in a safe manner. On this side, we have the onboard charging model that will handle the AC charging. Here, as you can see, it is connected to the outlet and to the socket of AC charging, and it will convert the AC into the DC power to recharge our battery system. We also have some DC-DC converters over here that will step down the voltage from the battery to 12 volts to power auxiliary systems such as the lights and the control modules and so on. And also this can be used to recharge the 12 volts battery that is the traditional lead acid battery of the vehicles. We have the drive unit, that is the electric motor, and we have the inverters that will work together to propel the vehicle and to transfer the electric energy from the battery into the kinetic energy to move the vehicle. And all of these, as you can see, they are marked with this high voltage component symbol. All of these need to be carefully designed for safety reasons and also for work together in the high voltage system. Besides the battery, the model, we identify that there are some components, for instance, the DC-DC converters, the AC to DC converters, and the DC to AC, or the inverters of the motor here. All of these are called the power electronics of the vehicle, and we will define them in the next slide. So finally then, we have as one of the big categories in our high voltage system components, we have the power electronics. The power electronics plays a very important role in the operation of the electric vehicles because they are going to be in charge of managing the flow of energy between various components. The power electronics has the responsibility of doing the energy conversion, and basically they will convert and smooth out the voltages that are needed in the different parts of the vehicles, ensuring that this is happening in a stable and reliable way to deliver the power as it is expected. Not all of the systems are able to work with high voltage level, so these converters will also manage the high voltage from the battery and convert it into the appropriate voltage levels that, for instance, the motor or the auxiliary systems can handle. They receive and process also some control signals from the vehicle to adjust the power flow and also to optimize the performance of the vehicle. The power electronics at the end will act as these intermediary systems to perform the energy conversion and will allow the energy to flow efficiently between the different electrical networks, such as the high voltage battery and the 12 volts voltage battery that is in the system. In general, we have three types of power converters. One of them is the DC-DC converters, and they are in charge of leveling a DC voltage, so converting a DC voltage into another level of DC. This can be done either stepping it up, it means increasing the voltage in the output of the power converter, or stepping it down, it means reducing the voltage. One example is, for instance, the DC-DC converter that are connected to the battery that will convert the high voltage from the battery, for example, the 400 volts, into lower voltage, for example, 12 volts to power low voltage components, as has been explained. Then we have another type of power converter, that is the DC to AC, also known as the inverter. The inverter has the functionality of transforming the DC current into an alternating current. Here we convert the DC power, for instance, that is coming from the high voltage battery into the AC power that is needed for the electric motor. The inverter not only adjusts the voltage, but also adjusts, for instance, the frequency and the intensity of this AC power signal, and with those variables we are able to control the speed of the motor and the torque of the motor as well. And finally we have the rectifiers, or the AC to DC converters. The rectifiers converts an alternating current into a DC current. In this case, for instance, we have the regenerative braking, that basically in that case we are converting the AC power that is coming from the electric motor into the DC power that then will be used to charge our battery. That is one example of this type of converter. So in a vehicle we have all three different types of converters. And with this we want to conclude this initial module and the introduction of the high voltage systems and high voltage components